Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to introduce you to the concept of velocity and what it means. So in this example here, I've got this picture of this car, and imagine that we start a clock here and we observe this car just driving along like so. And imagine that it's not significantly changing in speed. So as far as studying the motion of the car, first thing we have to do is have a way to describe where the car is at. So typically in physics what we would do is we would use a coordinate system for that. So I'm going to go ahead and put like a coordinate system right here. X, Y. Now this is a one-dimensional problem. I went ahead and put a two-dimensional coordinate system. Most of the problems we look at in college physics are two-dimensional, so I usually just start out right away drawing two-dimensional coordinates. But really for this example, this is the only thing we're interested in, is how the x coordinate of the car is changing. Now, before I move on with the problem of talking about velocity and position, we're going to talk about how to draw what's called a motion diagram for the car. So imagine a digital camera taking snapshots as that car moves left to right. Click, 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 and then superimposing all the pictures. What I'm going to do here is pause this for a moment and draw out what we would have. Okay, I'm back. So again, this car, imagine we've observed it move left to right at a nice uniform speed. And what I've done now is I'm drawing what are called motion diagrams, just snapshots in time. And what I'm going to do is I'm going to go ahead and label the change in position of the car. So X represents the position of the car. This distance, and I'll measure maybe basically from here to about the same point. That is a delta x, a change in position for the car. And if I measure another delta x, there's another one, and another one, and another one. And as we look at these pictures, you'll notice that these delta x's are basically the same. Now I'm just kind of freehanding this, but the delta x here is about that distance, and then about that distance, and this distance, and this distance, and so forth. So in this example, the change in position of the car is not significantly changing. So if we were to graph then position against time, and again that's the x coordinate of the car against time, here's what that graph might look like. I'll go ahead and draw myself a decent set of axes here. So again, we're going to graph the x coordinate of the car against time. So, depending on where the car was at t equals 0, I'm going to assume the car is here at some positive value. What that value is not super important for this example. And then as a time frame goes on, 1 delta t goes on, the car moves over a distance delta x. This is going to be some number. So basically on the graph we're going over and up. The amount over is a delta t, a time frame, and the amount we go up is a delta x. And then as another time frame goes by, we move over another delta x. So we're going to move over another delta t, up another delta x. And then as another time goes by, we move over another delta t, up another delta x. And when we connect the dots, we're going to get a reasonably linear graph in this example. Right now, when looking at linear functions, the important properties are the slope and intercept. Well, the intercept represents, that's this distance on the graph, and it represents where the car is with respect to my coordinate system, when I started timing this car. And then the slope, right? Now remember, slope is rise over run. If I pick any 2 points on this graph, maybe say this one and this one, that is a delta x, that's your rise. This is a delta t, that's our run. Therefore the slope is going to be delta x over delta t. And this is what we call the velocity of the car. So I like to define velocity like this. Velocity is defined as rate that position changes. In this example, the velocity is basically constant. You'll notice if I pick the slope of the line between these 2 points, or maybe this one and this one, or this one and this one, I'm going to get the same value. And again, that's just in this example. Since the slope is not changing, we say the velocity is not changing, or we say the velocity is constant. You'll notice in this example the slope is positive. That means that my car is moving in what I'm defining as the positive x direction. If the car were to start over here and go backwards, then this line might look something like this. We'd have a negative slope indicating that the car is moving to the left. So velocity is the slope of a position graph. Right? This is how it's defined. Rate that position changes. This is how it's calculated, delta x over delta t. Now what we're calculating here is what's called the average velocity. I'm going to make another video that talks about the difference between average velocity and instantaneous velocity. I think that's pretty much enough for this one. So everybody have a great day.